interest and interesting. What I'm going to do first of all is, I mean, obviously that's myself. I don't know how many of you have heard of us. Oh, we've still got loads of people coming in. It's great. I don't know if you've heard of the Stress Group. It is a little group of companies, as you'll see in a minute, based around Stress UK, or Structural Repairs and Specialist Services, which is the company I set up just over 30 years ago. But as the years go on, and with the sorts of things we're interested in, it expands into other things. And so within the Stress Group, we deal with geotechnics and have developed a specialist ground permeation system for strengthening the ground and underpinning. We deal with heritage engineering, so that can be anything from an old bridge to a monument or a church, listed buildings, things like that. We love solving problems with those, through to standard underpinning and all the sort of structural repairs and bits and pieces that go with it. But today we'll give you a little flavour of some of the more interesting projects we do and the kind of variety of things that we get involved with. The permeation engineering side of things that we do, we have an intellectual rights company called GeoInnovation.
Dave, I think you've just gone on to mute.
Is that me? Is that better?
Yeah, that's better. Yeah, I just clicked on.
I wonder why that did. Do you know when that went? Did that go quite early or just then?
Just last few seconds.
Oh, right. Okay. So we're back. So we've got the structural repairs and specialist services with different disciplines within that. GeoInnovations is an intellectual rights company that we have where we do research and development into new techniques for ground stabilization. And then we license those back to Stress for the sort of techniques that we use there. And that's, if you wanted it, that's a completely different CPD seminar. Goldhawk is a company that we bought in 2012 from Helifix. You've probably heard of Helifix. And Ancon is when they were joining Ancon. And Goldhawk basically strengthens bridges, but it uses masonry reinforcement, and that's where Helifix comes in. It's a unique system, and we install that for highways authorities, Network Rail, Canal and Rivers Trust, and anybody really who's got a bridge asset that requires it to be strengthened. Masonry arches, that is, not general bridges. So that's us as a group. So you've probably heard that we're relatively specialist, and we love getting involved in weird and wonderful stuff, which you'll see as we go on. Right, I'm getting that. Okay, I've probably given you some of the background for that. These are our services that that's 2023. I haven't even updated it. It's 24. Nothing's changed really. We're members of the Association of Underpinning Contractors. Reforce permeation engineering is what I was talking about with this ground stabilization. Heritage repairs, listed building works, which you then obviously need design and access statements for. We kind of do all that sort of thing. Do a lot of work for insurance companies, and we love unusual, awkward and high value projects. For some reason that button's not working. So within the structural repair side, which we're going to concentrate on today, there is that standard masonry reinforcement. We're Helifix approved contractors. Crack bonding repairs, cosmetic refurbishment. We're going to look at that quite carefully today. Stone repairs, if you're dealing with old listed buildings, you're bound to have to deal with stone. And so you need techniques to go with that. And we give guarantees as well with any of the work we do. So let's get steamed into it with something that I think you probably all recognise there, be it loss adjusters or engineers, surveyors, anybody that gets involved in buildings of any age really, because you can get ground disturbance at any time, causes problems. And there are obviously other reasons that go with it. And that's the point. Try and find out what you think has caused it. and identify the cause before you really plan to try and put it right. And in this particular case, I think we can see some fairly enthusiastic parking has caused some fairly decent fractures in that property. Now, I know it's a fairly serious call, and we don't really know how that ever happened. And the reason I put it up is for two things. One is show you sort of things that can happen, the fact that we, in fact, do on a not too regular basis, but a fairly regular basis, do extract cars and vehicles from dwellings and buildings. And what you can't do is just pull that car straight out of that building without the risk of continued collapse of the structure. So in fact, part of our work is therefore to look at the temporary works required to stabilize the brickwork so that the car can be safely extracted, and then you can actually go forward and rebuild and repair the structure. So, as I said, find out what caused the repair, what sort of aesthetic issues there would be in repairing that structure. And we'll see some of the issues as we go through today. You need to disguise the repairs, because if you're a property owner, or even if you're involved in your office block in itself, and you needed some structural repairs, would you actually want to see them? Or would you prefer if they are blended in nicely so they can't be seen? So it's really important to try and think about that, the aesthetics, when you come down to specifying a structural repair. Can you use masonry reinforcement? It's very, very useful. And if you are going to use it, how much do you need? Don't put too much in. And of course, put all this down on a drawing, because if you're going to need to use it within a listed building, you're going to need to record all the aspects of the repair. So for those of you who haven't seen masonry reinforcement being installed, here's three very, very simple pictures showing you the various stages. So we've got top left, guy with the blue hat. He's actually using what's called a Hilti wall chaser, and you will see that coming up later in the presentation. Very useful tool. We've been using these for way over 20 years now, and they do a very neat cut, very accurate cut into anything, really, concrete, stone, brickwork. And the idea really is to very neatly take out the bed joint so that you can install the masonry reinforcement. That picture actually is with him operating. It's vacuum recovery machine, and you get very little dust come out of it, which is very useful when you're working around domestic properties. Guy at the bottom is actually feeding in, not helibar as it happens, but that's what's called Betinox, which is a ribbed stainless steel bar, also made by Helifix, which we tend to use more in bridges and larger structures. And he's feeding that into the slot. The chap above actually is John Heseltine. He's the general manager of Helifix, and he is pretending to gun the helibond or grout into the slot which surrounds the bar and bonds it with the brickwork. You can then repoint over the top of that with heritage mortars or sand and cement, anything that actually matches the surrounding brickwork. So that is really how it's put in. The design is completely different, obviously, but that is how it's installed. So know your building. Don't be afraid to use innovation. Particularly if it's a listed building, you'll be very afraid not to come in with new techniques, things that will improve the structure without necessarily removing a lot of the existing fabric, because that's what conservation officers hate. They want to see the fabric, no matter what history it is during that building, remain in place. It tells a story. And so try and work around that. But don't be afraid to use modern materials. Helifix, we use Helifix all the time in listed buildings. As long as it's carefully used, as long as it's disguised properly, it's a perfectly good method of repairing and strengthening bits and pieces. Involve that conservation officer early in your projects. Get him involved. Tell him what your options are. He will comment. He will say, no, I don't agree. You can do that. I like that. Tell me more about it. Let him know the pros and cons, and he'll come on board, or he or she will come on board and work with you on it. Very important. So let's just look at something very, very simple. A domestic property repair. This is very typical for those of you loss adjusters, surveyors, engineers dealing with insurance work. We see this all the time. Slight settlement of that left flank wall. We found out when we went in there and did the investigation. In fact, that those drain pipes that had probably been there since 1938 when it was built were never linked to any drainage. So they just literally poured into the ground. And of course, they've caused washout, slight settlement of that wall and cracking. And this is probably why it was rendered in the first place, to hide up the cracks in the brickwork, because it would have just been bare brickwork in the first place. So there we are. We've got a crack in this rough cast render. How are we going to repair it? Well, fairly simple. You could take the wall chaser that you saw there and actually run your bed joints through, make the cuttings straight through that render into the brickwork and install your bar. Perfectly legitimate structural repair, but you're never going to hide the scars of where those bars are going to sit on the outside. You will always see them no matter how good your guys are, and our guys are exceptional in actually matching things, but they will never ever match the rough cast render. It's been there, I don't know, 20, 25 years. It's had numerous coats of paint. You put a new line in, even if you're brilliant at it, it will always catch the sun somewhere and you will see those scarred lines. So what do we do in situations like this? Go inside. Now, of course, that means you're going to disturb the inside of the property as well. When you explain to the client that's what you're going to do, they're usually pretty receptive about it. So we went in there inside the bedroom, take the plaster off, most of it falls off, expose the crack, install what here is what's called a heli beam. That's 2 twin bars to bridge that crack. Resin bond. You can replaster, repaint on the inside, and you will never see it. So that's the beauty of that. Now, that is a solid wall, which means obviously that you don't have 2 different skins. But even if you do, those of you who know the Helifix standard details, you will see that in fact, you don't need to put a beam on both sides, on both leaves, inside and out. You can do them on one, and then you put ties through to the other. So if you're working on the outside, you can tie the inside to it. Perfectly legitimate result. Now, when you then go outside, all you need to do is some very careful cosmetic work to the render, making sure it's obviously not blown. If you've got a big blown patch, you've not got much choice other than to take it off. But in this case, you do some very careful little render along the crack, sponges, different grouts, that sort of thing, and then paint it. It's not invisible, but actually I go past this on my bike, cycling maybe 2 or 3 times a week, and different lights, it's very difficult to see, which I'm pleased about. So that's the art of structural repair, perfectly adequate structurally, but make it aesthetically acceptable. Right, let's go on to something a little more challenging. A listed building in a place called Hadnam, which is out in Oxfordshire. We were called in by a main contractor who we do a lot of structural repair work for, and his special projects division had this old pub, the Green Dragon, to refurbish for a client who'd bought it, and I think actually wanted to flip it as a dwelling. came across major problems with the as you can see the state of it. But the particular problem we were asked to look at was that gable wall you can see there on the left. It was waving about in the breeze, cracked all over the place, loose brickwork, and generally not looking very, very tidy. As you can see there, looking up it, the state of it. We were called in to say, could we repair it? And we said, we think we can. What are the alternatives? The alternatives obviously were to take that wall down and rebuild it. Conservation officer wasn't going to have that. And the client didn't like the size of the bill he was going to get for that either. So we were asked to put a scheme together for it, to see whether we could actually save that wall, structurally enhance it, make sure it was good for the future. So what do you have to do? Well, as with anything, there's nothing particularly wonderful about this. You make sure you've got drawings and drawing records for it, particularly if it's a listed building. These have to be then part of the archive so that everybody can see what has been done in the past. But this was the gable. Normally we'll do it on CAD. This particular one, because it's interesting, was actually done quite quickly on architect's drawings so that they could be agreed with the client and the conservation officer. So you can actually draw on everything you're going to do. They also act as drawings for your crew when they go on site to know exactly what it is that they're going to do. Plan of that gable wall. Now the interesting thing here is where I've got that little handwritten note on the top right hand corner is a standard detail that isn't used by everybody. What we see a lot of the time is specifications for an angle tie that goes around the inside of the wall, so on both internal faces. Now the problem with that is if that flank wall, as we know it was, because it was rebuilt at some point in time in brickwork, was never tied into the flank wall of stonework, and hence it waved in the breeze. It was live. So if you're going to tie that in, best way to do it is to actually chase along the flank wall, drill through to the outside of the gable wall and return the bar on the outside. You then have the full tensile strength of the bar taken into account when you're tying it in. Just very simple details like that. Obviously, if you're going round on the outside of the wall, we couldn't in this particular case because it was straight onto a party wall into someone's garden and they didn't want to play ball. If, as you can see on the other corner, you go around the outside, that's always going to take the tensile stresses and strains. Still not working now. So there we are. Right, we're starting to put the heli bar in. Now, as you can see here, and this is another aesthetic point of view, that's stonework, fairly regular block size stonework, but you can see irregular enough to cause a bed joint that's not perfectly straight. So if we then cut using the Helifix wall chaser into that stonework, we would end up with bed joints that were straight in a wall where all the other bed joints are actually irregular, and it would stand up like a sore thumb. So in fact, you hand chase these out. We've got various tools we can use, but generally we'll use a chisel, hammer and chisel, and we'll actually chase out the bed joint to the right depth. You'll see why you do that in a minute. You can then still put the masonry reinforcement in. It'll follow all those little nice little lines, and you can surround it in grout. If you've got brickwork, of course, you can use that Hilti wall chaser. And the important thing here, and why I show this photograph, is if you're going to site, you've got one of these jobs going on, and you want to see what the contractor's doing. These are the tips to look for. Are the bed joints clean? Because if you've got any mortar in there, you're bonding then to the mortar, and we know mortar in general is fairly weak. So you want to be brick to brick face. You've got to remove all the mortar over the depth of the slot you need, 25, 30 mil maybe, and the full height, so that you've got brick to brick face. That slot should then be washed out, first of all, so hoovered out, then washed out, then primed, then the bar goes in, and then you surround it with Helibond grout. And then you know you're going to get brick to Helibond grout surrounding the bar to Helibond grout to brickwork, and the brickwork will then transfer the load into the bar and you'll prevent cracking. So that's the secret of it. If you see the photograph on the left, that's the inside. Someone microphone just come on. Thanks, Jamie. There is that internal corner we were talking about where they'd rebuilt the gable wall in brickwork, never tied it into the flank wall. That was part of the problem. It was waving about. So those lines on the left that go in the stonework go all the way through to the outside and then returned. We did stiffen the inside of that wall because you can imagine it's got a chimney in it. It's got at least one flue and a lot of hollow brickwork there. So to tie that all together, help stiffen that whole wall, we actually put Helibar on the inside as well. This gives you an idea then of when it's completed, that you see in that stonework, it's very, very difficult to actually see where we'd actually put Helibar. In the straight brickwork, you can actually see slightly different coloured. Yeah, the brickwork on the gable wall there, you can actually see a bit of slightly different, some straight lines, but that will weather down. We've used a lime mortar to try and match up with what's there, consistency, and that will weather down over time, and you won't be able to see it. But in the stonework, where it's slightly irregular, you need to be really careful. And as you can see there, when it's completed, it's looking pretty good. So there we go. In fact, there's a heli beam running under that right-hand window you can see above the glazed extension, ground floor level, because they needed to extend the opening. There was an old steel in there, and we helped them do that by putting a heli beam under that right-hand window on the rear, which meant that they could just do lightweight propping, get the steel in really easily. They put more load on that right-hand corner, but of course we just underpinned it, helped them out, take that load. But a very successful little project. Right, we're going to change something quite different now. For those of you who've been to Brighton, you may have been here. This is Brighton Royal Pavilion, and we're going to look at specifically that balcony you can see there at first floor level, which is the Adelaide balcony. So let's have a little bit of history. King George IV commissioned John Nash, I think an architect's name you will pretty well know. He was involved in all sorts of bits and pieces in London and for fairly high-flown people. King George IV came to him and said, look, I've got an old pavilion, an old villa down in Brighton. I'd like to use it to make something really quite extraordinary that I can show off to all sorts of dignitaries around the world, and be a place of sort of sanctuary and calmness. John Nash had noticed at the end of the 18th century that there was a new product called cast iron, which was coming on the market for extending structural openings. And he realized that by doing this in the pavilion, he could get greater spans, bigger spaces, much more elegant structure at the end of the day. And so he worked into it using this. These are the things that you will know John Nash for those of you who've been to London or live in London. Very famous for a lot of rather monumental structures. So he looked at, so you can see, back at the end of the 18th century, he looked at the first type of building that was using this cast iron, which was the flax mill up in the North Midlands. And you can go and see this. It's a museum at the moment, which was an industrial building, obviously a mill, a flax mill. And you'll see in a minute just how it makes a difference to the opening space that you get. Can you imagine the old days there'd be either brick walls or there'd have been big timber columns, timber beams, timber floor, everything bounced around. And by using cast iron, you can reduce the slenderness of the columns. You use jack arches. If you can look up there, jack arches being cast iron beams with curved brickwork, transferring the load of the floor into the beams. So that's why he wanted to use it at the Royal Pavilion. There is, however, a problem with cast iron. For those of you who have probably smashed a cast iron grate, you know that if you hit it hard, it will shatter. Which shouldn't really be a problem because most beams and things aren't going to get hit by a hammer. Might get hit by a vehicle if they're at ground floor level, but they're unlikely to get hit by anything. But of course, they get brittle failure. And what happened back in the early 2000s was that a roof collapsed in Bayswater, a roof that was supported by cast iron beams. And so it put a scare amongst all asset owners who had cast iron elements in their structures. And we'll find out why you get that unreliable parameter with it, which is this. You don't know whether it's actually going to go or not, or exactly just how strong that cast iron beam is. And the reason is the way it's cast. So you've probably seen this on TV. They'll make a mold in a sand pit and then pour the molten cast iron into it. Now, while it's still molten, of course, gases are rising up to the flange, which is the top at the moment, and they will bring all the little impurities with them. So actually, where you want most tensile strength, you've got a relatively unreliable and contaminated area of the cast iron. So when you turn that over, you're not quite sure just how pure that cast iron is. And so what happens is it maybe get overstressed, there may be an age issue, but it will suddenly fail, and it fails in a catastrophic way. So concerns were raised at the Brighton Royal Pavilion by the owners, and they brought in the same engineers who'd looked at the Bayswater collapse, John Holden Associates, who went and analysed the beams that are there under the Adelaide Terrace and realised, in fact, that it was cast iron of fairly poor quality, and therefore there was a risk. That balcony is used for the public. You can go out there. You may have been out there. There's a restaurant, and sunny days, there's tables out there. You can go out and sit on that. It's used for weddings. It's used for government and commercial parties and things like that. So you can have anything up to a couple of hundred people jumping about on that balcony. There was a problem. You realised that nobody quite knew exactly what the capacity of that balcony was. And so they had to prove it. That was the shortest, simplest thing they could do while they looked for a solution. So you can see here the centre line of props that were put up to halve the effective length of those beams, which are running between the wall on the right and the column and beams on the left. And this is where we were called in because we'd done quite a bit of work for Brighton Council on some of their listed buildings down there, and they said, do you have a solution for this? So we looked at it, we looked at all the information that we could find, and we came up with a selection of remedial options, one of which was to do nothing, but then you risk collapse, or you just don't use the balcony at all. That's really unacceptable. It brings a lot of money in, and therefore they couldn't have that. You could install some, secondary beams, as you saw the propping in place there, and have that as a permanent setup. But of course, it's listed. I mean, this is grade 1, 2-star gold diamond building, listed building, and so it's got to be repaired. It can't be left with various props and bits and pieces in place. So we thought, how about some carbon fiber? I don't know, for those of you who have actually seen carbon fiber plate, it's incredibly stiff. And as you know, it's used for all sorts of purposes. Very strong, very light. Wouldn't that be a perfect thing to use at the Brighton Pavilion? Remember me thinking about innovative ways of strengthening. We had a word with the conservation officer, and he said, interesting. We then said, well, we want to look into it a little bit more. And what we realized was that you have to glue that to the structural element to add the strength to it. And the problem with cast iron is, as we said, it smashes or it fractures. It doesn't bend, it just fractures. This isn't very good in shear. It's designed for tension. So to get that tension into this plate and get it to therefore shed some of the load in the cast iron beam, you need to make sure that this is in tension when the beam is loaded. Okay, well, the beam doesn't deflect, so it's never going to be in tension. So you have to cool the beam down so that it shrinks, then add the plate, and then allow the beam to expand to put that under tension. But the problem is you've got to put that cast iron beam below 0 to get it shrink enough. And of course, then the adhesive, the epoxy adhesive that you use to bond this to the beam will not cure. So you have to allow the temperature to come up, beam expands, and you might as well have used duct tape. So that, unfortunately, isn't a solution. But what if we used carbon fiber fabric? Not on the beam, but on the brickwork. So we make that jack arch brickwork that goes between the beams, we make that span laterally rather than span from side to side into the beams round the arch. And that was the idea that we took to them. Carbon fiber, we know, is used for all these sorts of things, and it's a biodirectional, usually a biodirectional filament in the fabric that's used. We don't want that because we only want to use this sheet in tension. So we're quite happy to have all the fabrics run in one direction, like the plate. That all they're less than 0.3 of a millimeter filaments all run in one direction so that you get maximum tensile capacity, but they're not in a sheet, they're not bound together with the epoxy binder. Obviously they're loose. This one's woven, that's bidirectional, but the ones we use are monodirectional. As you can see here, it's got a loose weave in it, so obviously stop it falling apart, and then it can be used to adhere to any structure. Colin Toms and Partners originally came up with a design for strengthening jack arches, and this is what was used by our conservation engineers, CTP, and they again do a lot of work for Brighton Council and came on board with this. They're actually heritage engineers, deal with carbon fiber, and so they were ideal for doing the design. And what we ended up with were 2 strips for each arch, 200 mil wide, full length of the brickwork arch on each of the jack arches. Listed building, absolutely priceless. Behind at the ground floor, behind those props there on that wall and through the windows, is the King's Apartments, and they are full of priceless artifacts. And so obviously Brighton Royal Pavilion are paranoid about water, dust, fire, obviously, vibration, anything that will potentially disturb all these artifacts. And they wanted to obviously keep the museum open as well. It brings in revenue. So we had to be very careful. Everything gets wrapped, fireproofed, and encapsulated. So we had a full working environment, protected from the outside and protecting the rest of the building from anything that we're doing. And here we are. We've got the scaffolding in place, all with fire resistant boarding, everything wrapped in fire resistant blankets, and ready for the off. So again, going back to listed buildings, you have to record everything you do to it, everything you find. So each of the cast iron beams was given a number, which you can see there, black, with tape around it, and each of the brick arches was labelled as well. That means that when you expose them, you can record exactly what you find to the number. Now you can probably see that good old Hilti wall chaser again. We use those because we can control the width of the cut and the depth very, very accurately to less than a millimeter. And so obviously what we wanted to do here was only take off as little of the render that was on the underside of the brick arches as possible. Because again, one of the things with listed buildings is the conservation officer will only want you to remove the absolute essential amount of material. Leave whatever can stay, should stay. And so we actually literally tried to take out slivers 200 mil wide. Well, they were 300 mil wide because you want 50 mil either side to be able to get the material in. 300 mil wide and the length for each of those arches. What we obviously found was that a lot of that render had debonded and it fell off. But you can see here on the left there, that biscuit of render that was left in the middle, we had to keep it and we had to match to it. So here we are, we've exposed the brick arches. Now you can see that in fact, not only is it brick, there's a bit of stone there. And these are sort of surprises you find when you uncover things, that they'd use bits of Portland stone into the webs of the beams. We presume because a brick just wasn't quite the right size, and so you could have stonework cut to fit tightly in there and to keep compression in the arches. You can see those beams are 5.4 meters, and there we are, fully stripped off. A lot of that render fell off, so it wasn't really doing anything other than just hanging off the surface or the underside of the brick arches. We then obviously clean up, and we've got ourselves a nice working environment. Now, for those of you who haven't dealt with carbon fiber before, I'm going to go back to that plate. To make this work on any surface, so in other words, mostly this is used to adhere to the underside of reinforced concrete slabs and beams. But if it doesn't bond to the concrete's never going to be able to distribute the load into it. So you have to do what's called pull-off tests. And here we are testing the brickwork, because again, if that brickwork couldn't transmit its load to carbon fiber sheet, you might as well use duct tape. So we need to check the bond. And these are little 50 mil diameter dollies. It's about 2,000 square millimeters on each area on each. You glue it to the surface and then you try and pull it off. And as long as you reach a minimum of 1.25 newtons per millimeter squared, in that pull off, you will fully mobilize the tensile capacity of whatever you're going to put on the surface. So we went round and we tested in various areas and got really good results. I've got to say, it was amazing. So before we started then putting the carbon fiber on, we then jacked a little bit of load out of the balcony itself. So each of those props had a little flat jack put on the top. And you've got Annie here. She's our conservation manager, and she took charge of ensuring that we had 8 kilonewtons in each of the jacks throughout the project. That just takes a little bit of deflection. I know I said they don't bend, but you still get a little bit of deflection in the balcony, and it was enough then that once we removed those and you get that little bit of settlement of the balcony, it will put the fabric under tension and the fabric will then immediately start helping the brickwork. So we got ourselves this laboratory now, and we have to cut the carbon fiber sheet. This was a few years ago. You can now get sheet in various different roll widths. In this particular case, we had to buy it at 0.5 meter and cut it down to 200 millimeter strips. So it's a relatively easy thing to do with shears, and you just you run along there and do that into the rolls you've got. You then need to make sure that your brickwork is perfect, because if there's any dust on there, for those of you who've got a, I don't know, you've cut your hand, got a dirty finger, because you've been gardening or whatever, stick an elastoplast on it. Elastoplast doesn't stick to mud. Well, it doesn't. Carbon fiber won't stick to dusty brickwork either. So the brickwork has got to be really clean. So it's cleaned and it's then primed. So you actually put a primer on it. But what you then find, if you put a straight edge to it, is there's lots of little variations between the bricks. They're not quite at the same angle. They're not quite the same height, which doesn't really matter structurally. But when you're trying to stick something to it, can you imagine sticking a wallpaper to badly plastered walls where bits of plaster are missing? You get debonding, you get holes where the paper isn't attached to the plaster. And as soon as you start doing that in brickwork, you're reducing the effectiveness of the carbon fiber. So you have to make sure that you're sticking to a uniform surface. So unfortunately, even on decent brickwork like this, you've got to put what's called a regulation coat up, regulating coat. Here we see one of our technicians, John. He's worked for me for over 25 years. He's a master screeder, master plasterer, and probably the only guy I've ever seen who can make epoxy putty do what he wants it to. And so we are bonding a very thin layer of this epoxy putty to the underside of the brickwork, which means it will take up all the irregularities and provide a nice smooth surface then for the carbon fiber to adhere to. As we can see here, that in fact we are about to lay on 21 sheets of layers of carbon fiber sheet. Don't know why it wasn't 777. We ended up doing 9, 9, and 3, but there we are. And you put it on with, as you can imagine, a fairly low viscosity epoxy resin. We use blue only because we could see where it was, no particular reason. Normally it's sort of a honey color, and it's fairly low viscosity, so it will soak through the carbon fiber sheet, and you end up with a complete monocot of carbon fiber and cured epoxy. When you've put one sheet up, to make sure that it's bonded tightly to the one above, you use a sort of rubber squeegee, and you pull it through, and of course that squeezes it tight up to the layer above, and make sure that you get resin passing all the way through. You then go wet on wet. So you put those 9 layers up, and then leave it and move on to the next one. Because the more wet you've put up there, the more that's hanging while it's curing onto that first layer that you put. And if that first layer doesn't bond, you might as well not have bothered. So you do it in layers, let it cure, and you can get there. So there we are. We've got all the beams now strengthened. So the next thing is to do the aesthetics. So this is kind of almost the most important bit in terms of the listed building work. We've got to now put back the render that's missing. So you put a scratch coat up. We obviously had the render analyzed, and what was amazing, because we imagined it would be a lime render, it wasn't. It was sand cement. So it must have been done within the last sort of 30, 40 years. They didn't have a record of it that we could find, but we matched it. But they did allow us to put what's called SBR in it, which is an additive that makes it slightly more sticky. So it will bond much better to the substrate and to itself. That's a scratch coat. And as you can see, that master plasterer of ours, John, did quite a remarkable job in matching up the render on the underside of it. And when it's completed, it looks like that. So the Adelaide balcony is now strengthened with carbon fibre. It has a factor of safety in excess of 2, and they can use that balcony quite happily, jumping up and down on and partying. So a very happy client and a very happy conservation officer. But these sorts of heritage works will go all over the country to do these, and we can help anybody who's dealing with it. We can help with design and access statements and making sure you can get listed building consent for those who get problems with that. But we love unusual projects, as you'll see. We're gonna go on to structural repairs now. Sorry, I don't know why button's not working. So this is, if you've been to the Isle of Wight, you may not have been here. It's called Core Abbey, Q-U-A-R-R, Core Abbey. It's a Benedictine monastery. It was erected turn of the last century, something like 1904, for a few years by some French Benedictine monks that came across and decided they were going to put themselves on the Isle of Wight. It's an extraordinary place. I mean, this is artistry and brickwork. It's fabulous. And it's been great up until a few years ago when they started finding they were getting cracks. We think through foundation movement, we can't find any other explanation. But the problem was that they were getting mortar and bricks dropping out of the arches onto the main aisle. And that's used obviously for the monks to pray 2 or 3 times a day, and the general public who pay to come in and have a look at it. So it became a health and safety nightmare. So we were asked to come in and have a look and see what we could do to make it safe. Rebuilding wasn't an option really, just to make it safe. And so we designed a system of tying plates, helibar, pins, and resin bonding to hold the whole thing together. You can see the height of these things. I think it's 12 meters to the crown. We couldn't put a full scaffold up, which would have made it very efficient for us to get to each of the arches. We had to use a tower, which slowed everything down. It meant that when the prayer was on, we could move it to one side. We could go down in the crypt and work on the arches down in the crypt. So we didn't have any downtime, but you can see the sorts of movement that we're starting to get in the building. This is in the crypt. These are much smaller Gothic arches. When you get that much movement, you can't hide it. So you have to do some rebuilding. And as you can see here, that's our arch rebuilt on the right-hand side. And what we then do is incorporate the helibar into it whilst we rebuild it. The pins and everything are all in there, and plates, so that it can move a little bit without, it might get a little bit of mortar dropping out, but it will distribute the load around the arch away from the crown and prevent that sort of splitting that you can see there. That's a flattened version of what we see, but well worth going to have a look. It's a stunning place. So I'm now going to take you onto another historic project, slightly unusual also in Bath. A lot of you will probably have been to the Roman baths. This is a project right beside the Roman baths and involves it. So you will probably have walked around the area, and that is York Street. You can see it going, left-hand picture there, going through and under that arch. And the wall to the right-hand side, the right-hand picture where those two ladies are walking past, is actually the dividing wall. That is the Roman bath. So if you climbed that wall and looked over into it, you would see that main exhibiting Roman bath, the outdoor one. So that's how close we are. Now the problem with York Street was that it's a modern invention. It was raised from a whole story below on the old Roman level to that level by the Victorians, who equalized out a lot of Bath so that you got all the shops at the same level, up above all these Roman remains that were down there. And of course, what they did was they used a composite beam or series of beams to support the road and concrete jack arches. So very similar setup actually to the Brighton Royal Pavilion, but this was steel beams surrounding concrete. But the problem is, of course, they're over 100 years old. We start to get corrosion. You've got very warm temperatures from the sulfur springs that feed the baths. You've got moisture coming in from the road through lack of maintenance and just general seepage, probably coming down through foundations also into the area. You therefore get corrosion of the steelwork. And it got to a stage where they couldn't be certain what capacity they'd got. So they shut York Street from lorry loads and any sort of traffic. It became a pedestrian area, which is nice for pedestrians, but didn't help with bringing lorries in to stock shops and that sort of thing. So they turned to us and said, have a look at this. What can you do? So this is what it looks like below. So York Street is above you there, and you can see those grey composite beams supported on Victorian walls and columns that have been built out of all sorts of old stonework they found lying around, a lot of which was quite old and probably Roman. Bits of Roman wall there you can see, and what you're looking at on the floor is actually the Roman pavement, the old Roman pavement, which is covered in sand for protection, but actually you can find all the flags down below if you're allowed to dig down for them, which we weren't. So that's what we're dealing with. We've got bits of old Roman temple and Roman wall that's got to be protected while we're down there. And in cross-section and plan at the top, cross-section with these three sections you can see below, gives you an idea of what we're dealing with. Now, the Roman baths themselves are just at the top of the plan. So you can see those two curves and that center rectangular cutout. Those are, if you've been to the Roman baths, those are those recesses that you can stand, have your photograph taken with a centurion or peasant, whichever you fancy. And that is the dividing wall between the area that we've got to work and the Roman baths themselves. And you can see that there's some of the beams actually extend through into the Roman bath area. So that meant that we couldn't really remove those beams and replace them because we've done too much disturbance and noise to the Roman baths themselves. And because it brings in so much money, they couldn't afford to shut the Roman baths and let us carry out the work. So we got permission from the archaeologist to erect a scaffold. That wasn't easy in itself, because you can imagine all those stanchions are sitting down onto the Roman pavement. So we had to protect it within an inch of its life. Scaffolding gets off, you've now got yourself a working platform. You can see the beams, you can see the columns, and you can see those dividing horrible concrete block walls that are dividing you from the Roman baths themselves. We had to monitor for vibration, and if the vibration got too high, they would stop us working. So off we go. But you can see that not only down there are the pipes, there's power cables, services such as water and gas. There was even fiber optics down there. So we'd have to work around all this sort of malarkey when we were working in there, and to come up with a scheme that could get around the problem of corrosion of those composite beams. Now, those composite beams actually were two I-beams butted together, surrounded in concrete. The mistake the mistake the Victorians made was to not infill the void between the flanges. So it was allowed to get moisture in there and corrode. And so we were getting corrosion mainly at the ends, and nobody knew quite how much. So we had a bit of a look, and we looked at over one of the columns so that we could get an idea. Yeah, okay, that beam was a little bit corroded, but really not too bad. But when we looked at the ends, which were open, that's where the corrosion was. And so the end bearing couldn't be relied on. So this is the solution that we came up with, which was to bond and bolt two galvanized steel C-sections to the existing beams. Now, the two C-sections would do all the work they were required to do to fully support York Street if the old Victorian beams failed. And that meant we could bring in new beams, clamp them to the existing beams with very little disturbance to the Roman baths or the Roman artifacts below us, and get on. But practically, this was not easy. Here's a typical beam. It is one of, I think, 14 we did. Each were different length, slightly different angle, and you couldn't make one template to work each one, because we've got to put holes through all those. So each individual beam had to be templated, and we had to bring the steels in 3 sections for each side of the beam because of the length, about 7.5 meters in total. We just couldn't physically get anything bigger than about a sheet of ply into that basement, because you couldn't come in through the Roman baths. That would have been too disturbing. You couldn't come in through, shall we call it, the tradesman's entrance, because it was like the maze at Hampton Court. And so, in fact, we had to use a manhole in the street to bring everything in. So it had to be limited in length and size and handleable. So we set about drilling. There are over 1,500 holes that had to be drilled in exactly the right position. So that template was used to mark it, and an exactly the same template went to the fabricators to drill the holes in the steelwork. Then it went off for galvanizing and then came to site. So these drillers did a really good job. They're not used to this, but they went through concrete, steel, void, steel, concrete, and they had to be accurate because that bolt's got to go through and it's got to match up both sides. We wore bump caps, although that chap's not wearing it for health and safety reasons. But in fact, as you can see, nothing can fall on you. We took samples of the Victorian steel. As you can see here, it's nearly 17 millimeters thick in the webs. And actually very little rust, as you can see. It was the ends that that, as I say, of the beams that were the problem. Now, when we're going to well, not necessarily adhere, but we're going to bolt onto the sides of the Victorian beams, these two C-sections, they have to be normal. And they weren't. The sides of the infill or the surrounding concrete from the Victorians was all over the place. It didn't need to be neat. So the shuttering had moved a bit. It was irregular. So we actually regularized the whole thing so that we could bolt and we get the two C-sections absolutely level and vertical. So we actually used, we set those little bits of galvanized, you call it bat strap, in the perfect vertical position, longitudinally and vertically, and it meant then we could render over it with a structural repair mortar, high build repair mortar, and that's what we see going on there. So, talk about access. That's York Street, and that was our access through a manhole. So everything had to go in through there. You can see the sections. Each individual set of 3, make sure they're well labeled, and they get lowered down at the same time. Slid down into position, onto the scaffold deck, maneuvered, and we use these very lightweight little scissor lifts to lift them into position and bolt them. A lot of accuracy needed to make sure everything joined up. And then you dry pack the bottom over the columns and the tops again to make sure you got full contact with the column and the concrete above. Now remember that the Victorians had left a void between those two steels. It's silly to leave it when you're doing all this work. So we actually had holes drilled in the galvanized steel C-sections and left as holes so that we could then actually drill into the center and grout up that middle section. So it reduced the speed of corrosion of the two steel beams and made sure that everything really hangs on for a good 120 years or more. Because you're grouting over a Roman road, conservation officer and archaeologists were paranoid we'd get grout into the sand protecting the Roman pavement, and so you can see we used paddling pools and buckets and visqueen and everything to protect it. But it went pretty well. We got an awful lot of grout in. The grouting operation really took quite a long time. We didn't get any leaking out into the Roman baths, which was great. And that's it finished. And nowadays you can actually go down there. It's an exhibition area. As you can see, they've opened it up to show off various Roman artifacts that they found. And obviously a lot of schools go down there, and there's actually a little archaeological area that you can dig for fake artifacts. The kids at it. So again, a very interesting problem-solving exercise and fascinating to do. We've got something a little bit different now. Remember me talking about arches, brick arches. I'm not going to show you how we do our bridges, but we do know an awful lot about arches, and we were brought in by one of the insurance companies that we do a lot of work for, who had a problem. Now here is a culvert. As you can see, there's a bit's missing, and the idiot on the left is actually the client. And we wouldn't go in the hole. It was far too much of the arch missing, which you would say, well, probably all right. But when I tell you that his house back wall was sitting on the crown of that culvert, and this isn't an ordinary house. This is an old stone mill. It's 3 stories of half-meter thick stonework is sitting on the crown of that arch. So in fact, we wouldn't go in there. We used a GoPro on a stick to have a good look and have a survey of what it was that we needed to do. But we were asked Could we repair it with the house in situ? Could we do that safely? Because if we could, it meant they didn't have to decamp the client. Saves a lot in accommodation fees, and it meant that they didn't have to, because the alternative basically was to take down the back wall of the house, take down the culvert, rebuild the back of the house. You can imagine the problems there, particularly when that's a live stream that runs along the bed and has caused this washout due to some of the probably the flooding conditions that we're getting nowadays and the age of the structure. Basically got scour, it washed out. You'll see the sort of void that's being caused. Now that guy, if he turned his head to the right, you would see a void up there under his house, into which you could probably put a mini clubman estate. It's not small. Hence him taking risks he didn't need to. Now the stream runs, this is the back of his house. Okay. The stream runs down through the garden, round the corner of this building, down to where those two guys in orange are, and then it doglegs under that part of the back wall of the house and runs through and then under the road. So we had to design a safe system of work, because if we're going to put guys down there to repair that, we have to make sure that nothing collapses on them. And so a whole series of temporary works were carried out. We did the design, and then we had an independent temporary works checker to make sure that we weren't taking undue risks. And that beam rests from the road through to the solid ground beyond the return on the side of the house there. And we then bolt quite decent sized anchors into the wall, so that if any one part of the foundation decided to settle, we could spread the load through that beam of that back wall, and it would at least give our guys warning that something was going on to get out. And you can see the ties there that are also going through from front to back of the house. This is us actually in there. There's the propping. I didn't do too many of the photographs of us going in, but what we did was we used maybe props. They can take enormous amounts of load, and you put one of those every meter, which means you could do one a day. And it gave you the safety of working only 1 meter into the tunnel each time where you set a new bed of concrete, fast setting concrete, put your prop on it, jacked it into position, and put whatever protection up you wanted. On the right hand side there, you can see we're actually starting to rebuild the skirt, and we use concrete this time to make sure that it couldn't be washed out. As you can see, we're using helibar, and that is to bond temporarily various sections of stonework. We used all the old stonework we could. Not that it was listed, but it's just easier than chucking all the stuff that's in the stream away and then bringing new stuff in. You might as well use that to recreate the arch. We, of course, had to monitor it. So this was dynamic monitoring. We had a total station set up with targets all over that rear wall, and warnings would go off if there was any movement of any of those points. And we checked it, obviously, each morning, each lunch, before we went back in the afternoon and at night, and then compared it with the morning again. Actually, we got no movement at all. And there you can see just the ties that went through with some of the clamps and bits and pieces that we had. But that gives you an idea of the void that was under the back of that house. Just shows how good stonework is, or even masonry really, at spanning. Remarkable. But that was our problem. So that's what we kind of had to do. And these were some of the drawings. So you can see what we, in the bed of the stream, what we then had to do: dig out, bag, fast setting material prop, and get that into position. And once that had gone off each day, we could do the next section, then go in and rebuild. And that was it completed. I think we did this about 7 years ago now. And I think at the time it was about £250,000. We had to work within the stream. Reduced flow, as you can see, we pumped some of it through as much as we can as soon as it rained, because this was in Ramsbottom, so this is up in the northwest of England, and as we all know, we get plenty of rain up there. So yeah, we had to deal with some flood conditions, in which case we couldn't work, but each time safeguarding the fact that nothing could be washed away, and it worked pretty well, and we completed the job. Very happy client. Well, guys, I don't know what time it is. How are we doing, Matt, on time?
We are, yeah. We can open some questions up, or if anyone wants to hang about just to hear this last piece, then just give us a thumbs up, guys.
Yeah, can we see if you've got time? It's quite an interesting little bridge topic, which brings in the strengthening of arches and the stabilization technique that we use for stabilizing and strengthening fill.
Quite a few thumbs up there, Dave. So yeah,
I'll
give it a go.
I'll crack on. This was a bridge brought to us by Network Rail about 5 years ago now, and we went to see it, and it was frightening. When a freight train went over, or even a passenger train, you could see that arch deflect. We had a guess using a very crude pole that we had of about 10 millimeters deflection. Now, I don't know if any of you ever looked at arches, but if you see brickwork moving, it's quite disconcerting. They basically had a limit, even though they were putting freight trains over it, and I really don't understand how they were managing to do that, but they were. It had what's called a root availability 0, and they needed to be root availability 10. That required deflection to be taken out and for the arch to strengthen. So we then looked at potentially using our Mars system in Goldhawk to strengthen it. That's masonry reinforcement in the arch, which makes distribution of load much more effective and prevents failure of the arch. But it's designed to be flexible, so it's not designed to take out deflection. Because arches, when they deform, that's why they're strong, because they distribute load. It's only when they over stretch that you get collapse. So to be able to distribute the load around it in reinforcement is our secret of how we strengthen arches, because you make the masonry do more than it's designed for. But the problem was, there it is, skip through this bit, there's the dynamic monitoring of a freight train going over it. Here's the Mars design on the left, and what we realized we had to do on the right, which was stiffen that arch, make that arch far more dynamically stiff. Now, if an arch is going to deflect, as you can see from my hands, if you can see them, the haunches have to move out, and that's what had happened over many years. Because this is actually an old Brunel bridge. It was designed and built by Brunel, so plenty old enough, and with the weight that's been put on it as the arch deflects, so the haunches move out. And so if you can stiffen the ground that supports those behind it, you will increase the stiffness of the arch. And that's what we looked at. So we took Network Rail through our Reforce system. They liked it. They thought there was, because we can control resin, it doesn't go everywhere. It only goes a finite distance from the lances. We could actually stiffen that fill, assuming it was non-cohesive. So we had them take some cores, find out what the fill was, because quite often it can be rubble, clay, all those sorts of things. If it's not permeable, you can't strengthen it. So in fact, we found out it was sand, which meant we could permeate it with a specific type of polymer, which then strengthens it. So that's what we aimed to do. That was the first thing that we we aim to do. This is what the Mars system looks like. This was a setup. We don't normally put props in, but with that sort of deflection going on and guys working under there, keeping the railway open, which was the important thing, we put a safeguard in, very much like we did up at Ramsbottom. And here it is, and you can see the dynamic monitoring going on. But for those of you, and this is a little lesson in arch repair and strengthening, if you put a prop in an arch and continue to allow it to take load, the arch will buckle around that prop because you're not getting distribution. So if you're going to put props in, you need to allow the arch to move. So in fact, as you can see there, that there's rather a thick black neoprene gasket that is 25 mil thick and is allowed to compress. So the arch could still deflect, distribute its load properly, act like an arch does, but if there was a catastrophic failure, the props would come into play and give our guys time to get out. So that was a theory. It worked perfectly. So this is us. We've driven our lances to depth and we're now injecting. Now, to give you some idea of, for those of you who know geotechnics, you'll know in soils almost of any sort, the void ratio is somewhere between 0.3 and 0.35 probably, which actually means that between around about a third of the volume of that soil is void. Now, it can be filled with water. Quite often, if it's above ground, it's filled with air. So those are all the little interstitial spaces between the particles. Particles sit together and leave voids. A third of the volume of that soil is void. So we know we can get, if it's permeable, we can get a third of the volume of that material into those spaces. Now our material expands by about 2.6 under normal pressure conditions. So you take the void in the volume you want to strengthen, divided by 2.6, and that is the amount of literage you need to put in there at 0.3 roughly of the volume. So we know exactly how much we're going to go in. We know that this technique only allows the resin to go about 250 mil from the lance and stop. It then takes on the moisture that's in there and expands slightly and then gently pushes itself through the soil, so solidifies and strengthens the soil to somewhere around about 3.5 to 5 newtons per millimeter squared. And what that basically did was it reduced the deflection, that's the same scale, by about 2/3 from what we were measuring at about 6 to about 3, or just over 2. So that did enough stiffening that it meant that when we put the Mars system in, and you can see here all the cuts that we put into it to install the masonry reinforcement, when that's actually bonded into the structure, which is a whole other CPD for you, that was the deflection. So Network Rail were absolutely delighted. They didn't have to take one single train out of timetable. There it is now. You can see the lines where it is, but it's not particularly obvious. And it's being used today. And 5 years later, it's looking like the day we put it in. So a very effective way of doing things, looking laterally, no need to shut the railway down, no need to take half the bridge down, no need to renew it, because that was the option. That they didn't know any other way of doing it other than to shut the railway for a period of time, knock that down, bring in a concrete bridge which needed power foundations, and the disruption that would cause, you can imagine, the timetable cost. And of course, think about the carbon footprint of doing that little bit of repair and strengthening compared to a big concrete bridge and piles. Anyway, good. I hope that was interesting. Matt, if there are any questions, I'll be delighted to hear them.
Yeah, brilliant. Thank you, Dave. David Cantrell, I know you had your hand up just before Dave started speaking, so I'll pass it over to you if you've got a question or query.
if he's still there.
If he is still there, unless he's meant to do thumbs up earlier, not tomorrow. I know Terence had a few questions on the chat now, so let me just dig those up. First one, Terence asked, do you just provide the structural designs or can you act as principal contractor also?
Excellent question. We do we have our own consultancy side, so we can do structural design. Usually it's for design and build, so we act as main contractors. We've got main contractor status both in Gold Hawk and in Stress, so we can tackle anything from a couple of thousand to generally not more than about 1.5 million, but we act as full main contractor if required.
Brilliant. Thanks, Dave. Terence again just asking if we're on any framework for the London Borough of Hillingdon. I think
Yes, we are. I think we are, yeah.
Yeah, thought so too. Got another one from Kevin here. Just a question around permanence and future change. He's asked regarding reversibility of the resin, epoxy, putty, and carbon fibre solution. You're designing for perhaps 120 years. What happens after, and what are the alternatives, if any?
Do you know what? That's probably one of the best questions that we've had asked. That is a very, very good point. So at some point in the near future, and we have talked to Brighton about this, an examination will need to be made of part of the Brighton Royal Pavilion, and I guess any other structure that's actually got carbon fibre in it, to check the condition of it, the bond, and to make sure that it's working accurately. But currently, I'm actually on a think tank or in a think tank with a bunch of other people from around the country who are looking into this this heritage that we now have got from designs of buildings, a new type of building you would call it, where reinforced concrete is started to be used. So let's say we call it 60 years. I know it's probably a little bit more than that. Are we expecting these structures to last another 60 years? Can they? Do they? What's involved in actually making things right? We've got metal frame buildings now, not just steel work frames. They're a little bit easier. You've actually got metal frame modern buildings. How do you know that that galvanized tin that's used to make up the sections is still okay? How do you get to it? How do you repair it? It's a really good question. So from the point of view of looking at a bridge like this or Brighton Pavilion, it's lasted best part of 400 years. If you can extend its life by another 50 to 100 and then look at it, there will be other techniques in the future that you can use, or it could be that this particular technique, which is it should be completely inert, has no breakdown, there's no UV problems or issues anywhere. It could be removed if you had to. That's the point. And again, with the Mars system that you see on that bridge, you can take that back out again if you want and renew it if need be. Obviously, you've then got to put a certain amount of propping in if you want everything wants to be safe, or you shut the railway. But there's nearly always, I don't think we fit anything that you couldn't renew. Maybe the reforce system into the ground, that would be very difficult. It could all be dug out if you needed it. But it never needs to be. So a cracking question, and you've opened up just a huge problem when it comes to existing and future buildings.
Brilliant. Thanks, Dave. Paul Hacking, I can see your hands up. I'm just going to come back to you after, if you don't mind, just because there's a few questions that come in first. They should be quite quick to answer. First one, Dave, from Andrew Kennedy. Have you been involved in the Hammersmith Bridge project? Which I'm sure we have.
That I believe was either Fresnay or Concrete Repairs Limited. Yes, we have, funnily enough, because years and years ago, we put up an enclosure around one of the cantilever heads of the flyover, because they realized actually they could reduce the amount of weathering that's going on. Trouble is, salts are coming through from above, which I think have been dealt with now by the sealing of it from above. But putting on a protective layer around concrete or any building will actually protect it and stop it weathering. And you can literally stop the reduction in strength and weathering by actually putting something round. Having said that, we were never called back to do any more work on it. So yes, I have, but disappointingly, no, we've not been involved in anything more.
Brilliant. Thank you, Dave. Another one on the chat. Can these repairs be done on L-shaped precast retaining wall with crack around corner?
So this is coming down the vertical leg and then out onto the horizontal structural leg. We've done something very similar, but you're not going to get an awful lot of strength out of fairly thin bars coming down on a right angle where you're asking it to do that. It'll add a little bit, but nothing. You really want that bar to go into tension, and really you're only bending it. So no, I don't think it would work. I'm putting carbon fibre around. Maybe we're talking about that. Again, it's relatively stiff, but you're only asking whatever the strength is at the corner to do anything. So no, I wouldn't have thought so. What we do a lot of is to put anchors through the wall at an increased spacing, and then put masonry reinforcement between the anchors to spread what will become quite a heavy load at the anchor head. Distribute that into the wall. Yes, we do that quite a lot. Hope that helps.
Brilliant. Thank you, Dave. Just going to ask one more in this chat. I know there's a few more, and then I'm going to pass over to Paul because I know he had his hand up. But just one more for the chat quickly from Stephen. What primer solutions are used before the heli bars are installed in masonry?
It must be, it's a secret. Helifix, we just buy it as Helifix primer. I believe it's basically diluted SBR, styrene butadiene rubber. Basically, you know, the white fluid that you get looks like Unibond, but actually it's frost resistant. So we use it for outside, and it's the basis of a lot of polymer modified concrete repair materials and mortars and things like that. But yes, it's a solution of SBR, we're pretty sure. Just makes it slightly sticky, and the mortar bonds to it better. Again, that's the first time I've been asked that. Good question.
Brilliant. Thank you, Dave. I'm going to hand over to Paul Hacking. I know you had your hand up, Paul, so if you're still there.
Hi, Paul.
Okay. Thanks, Dave. That's very interesting. Coming back to Brighton Pavilion, why did you not run the carbon fibre reinforcement? You put it on the springs of the arch, but why did you not run it on the underside of the cast iron beams?
But basically, you remember me talking about the fact that it's not going to do anything. It's a bit, you might as well use duct tape or wallpaper under there, because it's not actually going to. It would adhere, but because the cast iron beams don't deflect like a steel beam, they don't stretch as they take load.
Okay, yeah.
They shear. So cast iron beam, there'll be a little bit of movement in it, and then you increase the load and increase the load, nothing happens, and then suddenly it shears. And of course, carbon fibre is not designed to take shear, it's designed to take tension. Simple as that.
And you wouldn't have put a new beam on the underside of the existing? Or was it just going to be too deep?
It would have been too deep, and of course it would have scarred the original design and style aesthetics of the Adelaide balcony. And basically that is an unacceptable method for the conservation officers. If you had to, you could. That's a bit what I was saying about putting the secondary steel in there. But yeah, not an option that is deemed to be acceptable from an aesthetic point of view. I'm sure if there was absolutely no other choice other than to let it collapse, then something could have been done along those lines, and you could have beefed those beams up. Yeah, agreed. But that was the reason.
Okay, thank you.
No, thanks for the questions. Nice to talk to you again.
Brilliant.
How we doing,
Thanks,
Matt?
Paul, and thanks, David. I've probably got one more in this chat. It was from David Cantrell, who had his hand up earlier, just regarding the Adelaide balcony. He's asked, how was the carbon fibre curtailed at the ends, i.e. adjacent to the bearings of the cast iron beams? How were the shear forces of the composite repair transferred?
Right, again, good question. I'd need to go back to the little diagram that showed how we strengthened the jack arch, and you will notice that we've got that little bit of stonework that sits in there into the cast iron beams, which is more irregular than the brickwork, and so it was the brickwork that we wanted to adhere to. So we came, I think, at least 50 mil up above the stonework. We then had that 200 millimeter band where the carbon fiber is going to go, and then another 50 millimeters of working area there. So the carbon fiber never interfered with stonework. It purely sat on the carbon fiber and strengthened that strip obviously on either side, as you say. Not quite the springing point. We're almost on the third point of the arches, and making those actors beams. So yeah, we did. And again, we weren't involved in the design on that, so there was a lot of logic to it for us, but we didn't query it. Hope that helps.
Brilliant. Thank you, Dave. I think that is everything in the chat. I know quite a few of you asked if there will be recordings of this session, and I'll share that though with that this afternoon. So yeah, this has been recorded, so I can share that. It's not a problem at all. But I think that's probably everything, Dave.
Oh, that's excellent. Well done, Matt. Thanks for organising, and thank you everybody for turning up. I hope it was interesting. Sorry if I sort of stammered and blurred a little bit. There's a bit of distraction going on outside, but that it gave you an insight into innovative thinking for structural repairs. And please, come back to us at any time if you've got a problem, anything you'd like us to look at. Any further questions that you suddenly think about, flip them through to Matt, and he'll get them through to me, and I'll very, very happily answer those, or try to, back to you via email. And yeah, as I say, talk to Matt again if you're interested in geotechnics or the Mars system for strengthening arches. Delighted to ramble on about that another lunchtime. Thank you again. Take care all. Bye-bye.